So for this round, we're going to use Jupyter notebooks to discuss the content, and so Jupyter Hub will be launching in the near future on Polaris. So this is kind of the interface that you will see. So you'll go to jupyter.alcf.anl.gov, and there'll be a button here for Polaris, and then you'll be able to log in. So I'm going to start a session on Theta GPU just for this workshop. I've already logged in. You would normally log in using multi-factor authentication, and I'll get a Theta GPU compute node, a single GPU, and do the STL workshop. I just want to note that it's possible to run Jupyter notebooks on Polaris as is now, but you have to use tunneling in order to get access to it. Let me start up the server. So right now, the server is starting up, and it'll automatically redirect me to the Jupyter notebook session once it starts. Could someone, I don't know if it's already been posted, but could someone post a link to the content in the Slack in case people don't know where?
Yeah, I'll post a link.
Right now we're pending in the queue. We don't have to wait too long. If we do have to wait too long, I'll just open a local session and we'll do the content locally. Wait a few more minutes here and see. Stop running. Oh, here it goes. So it starts off in this tree view. If you're more accustomed to the Jupyter Lab sessions or Jupyter Hub Lab sessions, you can go up here to the URL and change this from tree to lab, and we'll open up the Jupyter Lab interface. So already have the TensorFlow notebook open. So this is where we're going to start. Increase the zoom here so we can see it a little better. All right. Well, as many of you probably know, that TensorFlow is an open source machine learning framework. It's been developed primarily by Google and some others, and it's been released for several different languages. In this part of the session, we're only going to focus on the Python part of it, but if you are using some of the other coding models for TensorFlow, please just contact us at support@alcf.anl.gov, and we'll be able to assist you on getting that up and running on Polaris. The TensorFlow machine learning framework is well documented. You can visit their website if you want some more information about TensorFlow. In order to get started, you want to import TensorFlow Stf. One thing I'm going to do before I start, though, is I'm going to make sure that the kernel that I have selected is the latest one supplied through Conda. So on Theta GPU, it's this Conda 2022-0701. It might be slightly different on Polaris by the time we have Jupyter Hub running. But make sure you select the latest one. That'll make sure you get all the latest versions of the software that we have installed on Polaris. So this is importing TensorFlow now, the usual way. So one thing to note is for all these machine learning frameworks, they're built on the concept of tensors and using tensors as data types. And these machine learning frameworks support a variety of different mathematical operations on the tensors. And I want to emphasize that these notebooks where we're discussing these different frameworks, they're not meant to be tutorials on how to use TensorFlow, or I'll talk about Pytorch in a minute, and Corey's going to talk about JAX. These are just kind of showing you kind of the best practices and how to get best performance on Polaris. So with that said, assuming you have some some sort of familiarity with TensorFlow or these other machine learning frameworks. Let's discuss a little bit about them. So as I said, TensorFlow supports a variety of mathematical operations on tensors. In particular, it's out of the box supports GPU operations. So why don't we compare the performance when running on a CPU versus a GPU here on Theta is what I'm running on. So here I just set the device to a CPU device. We generate a random tensor with a shape 2 by 5000 by 500, the elements. And here I'm just printing out to show you where the data is located. It should be located on the CPU if we did this correctly. And we're going to do matrix multiplication of the data and store it in this new variable product. Here we're just doing a matrix multiplication of the randomly generated data that we did, and we're transposing one of the data types so that it can actually do the matrix multiplication. And we'll see where the data is located for this product. Should still be on the CPU. And then we're going to time it. So here we'll delete the product and we'll just do the timing of the mathematical operation on the CPU. So let's run this and see how it goes. As you see, the input data location is indeed on the CPU. The output is on the CPU. And the calculations were also completed on the CPU. It's still running the time operation. Let's look down here. It took about 16 milliseconds to do the operation. As you see, the output is in the dimensions that we expect. So we transpose this above array and it contracts over the 5,000 elements, and we end up with a 2 by 500 by 500 matrix for the product. So now let's do the same thing, but on the GPU. So as I just said, it's the same setup, but instead of with TensorFlow device CPU, we do GPU, and it should select the first GPU available. And as we see, the data is located on the GPU now, and the product data is also located on the GPU, and the operations were much faster on the GPU. And that's because the TensorFlow is able to take advantage of the parallelization of this matrix multiplication operator on the GPU. Now, this isn't the only mathematical operator available for tensors, as many of you know. So you can look through the TensorFlow documentation and see what's available. So let's discuss getting access to data. So later on today, we'll have a session on setting up data pipelines. So stay tuned for that. But for now, we're going to just use the CIFAR10 data set, which is available through TensorFlow. I believe it's hosted by the people who generated the data set. But anyway, this data set consists of 60,000 32 by 32 color images in 10 separate classes. And there are 6,000 images per class. So this just means there's 50,000 training images and 10,000 test images in the data set. So we can import it here by using this method available through Keras datasets. And we can indeed see that the training data set has 50,000 images. They're 32 by 32, and there's 3 separate color channels, RGB. And for the data labels, we can see that there are 50,000 data labels, and notice that there are in this shape 50,000 by 1. So it's like a column vector of the labels. I just printed just a little sample of the labels here. They're between 0 and 9 are the labels. So they are like dog, cat, bird. You can look at the details of the CIFAR10 data set if you want to know more. So this training data comes in as a NumPy array. So it needs to be converted to tensor objects. So if we just look at the type of the data here, we see that's a NumPy ND array. And its data type is unsigned int 8 for both the training data and the and the labels. So one thing we do is we'll do this in a batch, just like one batch of 10% of the data. So we convert it to a tensor, and we explicitly convert the data type to float 32 here, so we don't come up with any surprises during the mathematical operations. One thing to note is by default, TensorFlow uses float 32 for many of its default data types, but it is capable of setting the data type based off of the input data. If you're using NumPy arrays, it should do the data type of the NumPy array itself. So as I just said, we explicitly converted from the unsigned int 8s to float 32s. So since TensorFlow is a machine learning framework, it supports many of the well-known operations that are performed during machine learning, such as convolution, setting up dense layers, things like softmax, etc. They're all well supported. And one of the easiest ways to build up a machine learning network is to use the Keras API. So I put a link in here for that. To do object-oriented model construction for your machine learning networks. And for now, for this notebook, we're going to build a ResNet-like model here. So we start off by making the residual block in the ResNet model. So here we inherit from the Keras model class, and in the init step, we make sure we call the parent classes init so that we get all the functions that we need from the Keras model. And we also add 2 convolutional neural network layers, 2D layers. So there's 16 filters here, working on a 3x3 grid. And now we want to do what happens when you call this residual block. So here we apply the first set of weights, so the first convolutional layer, and then we apply the activation function. Here we're doing a ReLU, and then we apply the second set of weights, and then we perform the residual step here, and then we do the second activation layer. So that's our residual block, and now we want to set up the ResNet model. So again, we make a new class, my model, and we inherit from the Keras model. And again, we do the initialization. We got to call the parents class initialization, so we get all the functions that are required to run the network. And now we start with a convolutional layer to initialize the data, or to initialize the network. And then we do, here we're doing one residual block, then a second residual block, and then we do a final convolution down to the 10 filters, because there's 10 classes in the data set, or 10 labels, 10 different classifications. I don't want to confuse, with the Python class, David. Anyway, and then we pool we do a global average pooling of the 2D data for the final layer. And then, well, actually, I'm sorry, these are setting up those different pieces of the network. And then we want to actually do for the call, actually run all those different pieces. I misspoke there. So then the next step, did I run this one up here? Let me just run it again, just in case. So the next step is to create the model. So I just have some variable called model here, and my model. And we build it based off of the shape of the input data. This building of the model isn't strictly necessary. The only reason why I do it is so that we can visualize the model here. So you can easily do that with TensorFlow by using a print statement. So it shows us what's going on. We have a 2D convolutional 2D convolutional layer for the first step. And then for the second step is the residual block that we built. And the third layer is the second residual block, and then the fourth layer is this 2D convolutional network. And then finally, we do the global pooling, which gives us and it also prints out the total trainable parameters as well. Get an idea of kind of the computational load that's going into training the network. So we got a simple network setup. So talk about some of the other functionalities. So one big advantage of the machine learning frameworks is automatic differentiation. TensorFlow supports this through the gradient tape syntax. So in order to set this up, we need a loss function. So here we're just going to use a sparse categorical cross entropy. There's a lot of loss functions available in TensorFlow. You can go to this link if you want to look at them and see what they are. Let's get the loss function set up. And so here we are. We're using this gradient tape syntax. So you do with gradient tape precision equals true as tape. Then you get the logits for your model and calculate the loss based off those logits. And here we can get the normal derivatives with respect to the training parameters from this gradient tape. So to do that, you just do tape.gradient, and you look at the loss, and then you say model.trainable variables. You can also get the gradient with respect to other components. Say you wanted to track other components besides just the trainable variables. So one way to do that is to use this watch. So here we're saying watch the batch data. And again, we get the logits from the batch data, and we get the loss from the batch data. I guess the important thing to note is that when you do these gradients, the first variable is your loss. The second one is what you want the gradient of. So here we can get the input gradients. I'm not going to print them out, but you can see that it's in the shape of the input data. So you get the gradients with respect to the input data. So this is the important part of get good performance on Polaris. So let's talk about TensorFlow functions. Often the TensorFlow code will run faster if you graph compile the code. So let's just look at the gradient step here. So I define this function gradient step, which just does what we did above to get the gradients, but it's in a function. Let's just get like the base timing of what that might be. We're doing it the way that we had just done it before. So here I'm using this IPython magic to do the timing. And it took about 62 milliseconds to do that gradient step for the network that we have currently. Now, what's the timing if we graph compile it? So to do graph compiling, the simplest way is just you do TensorFlow function, and you wrap that function above with this TensorFlow function. Now let's take a look at the timing of this so-called graph compiled function. And so you see it's much faster, 1.4 milliseconds compared to 62 milliseconds. So you can get a lot of speed up just by wrapping your function in this TF function. This could be further expounded on. So depending on where you're running, you can take advantage of the so-called accelerated linear algebra libraries. So those are available to the devices. So this is available through Polaris. So we can graph compile the same function using XLA. In order to do that, you just use the same TF function, but you say JIT compile equals true. And we can time it again here. And you see, again, we get about a factor of 2 speed up here. It was 1.4 milliseconds before, and now it's hovering around 700 microseconds. Another factor that can improve performance is doing what's known as mixed precision math operations. So some devices allow for mixed precision calculations that are faster than, say, you're using like double precision throughout or floating precision throughout. You can enable this through TensorFlow by doing this import before you run your code. So from TensorFlow.keras import mixed precision. And then you can set the global policy to use mixed precision throughout. So you see, if I set this policy, it says your GPU will likely run quickly with D-type policy mixed float 16, as it has compute capability of at least 7.0. So that lets us know that mixed precision is probably a good idea here. So what happens if we try to do this again? Well, we would expect to see some sort of performance improvement. Notice that our performance is about the same. That's because I didn't import this before I compiled the model. So let me copy paste this here. So let's restart the kernel, go back to the top, and put this in. We'll just quickly run through these cells. Down to the timing, loss functions, or the gradient, sorry. All right, here we are, gradient step. Okay, so as you see, before we were using mixed precision, it took about 62 milliseconds to time the gradient step. All right, so about 62 milliseconds. How fast is it with mixed precision? That's about 24. So before it's about 3 times slower without mixed precision. What if we graph compile the code? So before it was 1.4 milliseconds. Let's see what we get now. It's about the same. So we didn't really see much of a performance boost during graph compilation. And what about with XLA? Here, I suspect we'll get some errors. Yes. These are warnings. Basically, it's seeing a difference. And this is because results mismatch between different convolution algorithms. And this is because of the reduced precision. So we expect to see some minor differences in the reported output because of the precision loss. But before, I think it was around 740 microseconds. Now it's slightly faster at 713 microseconds. Anyway, so that's kind of the best practices of how to gain performance on the best performance out of TensorFlow using on Polaris. One thing that you might want to experiment with is using this mixed precision, but definitely make sure you graph compile your functions if you're not doing that. Got a big speed up doing that. All right, so let's move on. Any questions about TensorFlow before we move on? It's looking like there's no questions. If you have any questions, please post them in the Slack, and we can answer them there. Let's move on to Pytorch. See how we can quickly run through Pytorch. I ate up a lot of time fixing my microphone earlier. So again, Pytorch is another machine learning framework. I'm just going to quickly go through this because a lot of this stuff is the same. You can get access to it on Polaris by again using forgot that I don't have. Oh, I'm using the wrong. See, this is why I need to change the kernel to the latest Conda kernel so I can have the correct software available. Okay, try again. So here we're going to temporarily load the CIFAR10 data set. We're going to get it from TensorFlow just like we did before. So we'll load TensorFlow and then we'll just delete TensorFlow and won't use it after we get the data set. Again, we're going to batch the data, and we're also going to permute the axes because TensorFlow likes to have the data in one way, and Pytorch likes to have it in the other. So so here now it's 5032 by 3, and after we permute, this is the batch data, but after we permute that RGB dimension is in the second slot instead of the slot. Anyway, again, we need to make tensors out of the data, so we do that here. And we're just going to leave the data types as is. Note that Pytorch convert, we're explicitly casting the labels to int64 here. So you can create machine learning models again, just as you do in TensorFlow. Try to quickly go through this. So here we set up a residual block. We inherit from the torch.neuralnet.module class. And again, we have to initialize it. We set up these two convolutional neural networks, or convolutional layers here, as you see. And instead of call, they use forward for the function calls. And again, we do the setting up of the layers in the order that they need to be called. So we do the weights of the first convolutional layer, and we do an activation function. We do the weights, the second layer, or the second convolutional layer, and then we perform the residual step, and then we do the final activation. And again, we have to make a model, or our ResNet model, built using these residual blocks that we just made. The same story here as before, but things are named slightly differently. And here we get access to our model, so we make a variable model. You can name it whatever you want. And again, you can easily visualize your network by printing it. One thing that Pytorch doesn't do out of the box is give you the number of trainable parameters. So I have this one-liner here that will get you the number of trainable parameters if you want to use it and print them out. That's a little more difficult to parse, but it gives a little more visualization of how the network is built compared to the TensorFlow print function. So here, before, recall the TensorFlow print function, we could only see the residual blocks. We didn't see these inner layers, which I think there is an overload that you can give to the print or a keyword argument so that you can see these. But you can see we have our initial convolutional layer, and our first residual block, we can see what the residual block's made of. Second residual block, you can see what it's made of, and then our final convolution in our pool. And this is, as we see, it's the same 9,514 trainable parameters that were trainable in the TensorFlow model. Again, you can do automatic differentiation using Pytorch. It's set up a little bit differently than the TensorFlow implementation. So you want to use this automatic differentiation package, torch.autograd. So here we so here we get the logits, from running the batch data. So we have 5,000 5,000 different inputs in our batch data, and we end up with 5,000 by 10. So this is the raw logits, right? So we print. Oh yes, to show you that the labels were still in this 5,000 by 1 shape. Now we want to do the set up a loss function. What's important here is that the loss function is expecting the labels to be in a certain shape. So we need to flatten these labels because the shape does not match up with the expected shape. So here we got 5,000 by 10, and we want to reduce the number of dimensions by 1 for the labels. That's why we flatten it here. And here we see the loss is 42. Particular case. So in order to do the gradients, so like I said, we use this autograd package, similar to the gradient tape method, but we don't have to use the width. So we do torch.autograd.grad. we give it the loss, and then we say, okay, we want the gradients on the model parameters. So looking at those gradients is a little bit more cumbersome in Pytorch. So I gave you this method. I only print the shape here because I don't want the gradients will obviously be very, very large, but you can, instead of printing the shape, you can just do some function on those gradients inside of this. So the model.parameters is an iterator over the parameters is what I'm trying to say. Anyway, so as before, maybe you want to look at the gradients with respect to some other thing besides the model parameters. So you can do that in Pytorch as well. So let's try to do it with the batch data like we did before. But you see, if we do that, we end up with some sort of error. It says one of the differentiated tensors does not require grad or doesn't require gradients. And that's because there are when you set up the tensors, you can mark them as requires gradient or doesn't require gradient. And in order to track the gradients for things that don't require gradients, you need to mark them as requires gradient. So let's do that here. So we run get the logits again, but this time when we pass in the batch data, we're going to set this member requires grad, and then calculate the loss again. And now when we try to get the input gradients, we'll get what we're looking for. This autograd function returns a tuple, where since we're only looking for one set of gradients over the batch data, we're just going to grab the first member just so we get them directly. Print out the gradients. Oh no, ran out of time for that session. But anyway, let me just mention you can do the same thing for performance. As before, so we can do the timings of the gradient step, and get better performance by doing something comparative to the graph compile. They don't have graph compile in Pytorch, but you can do JIT compilation and get better performance. So in order to do that, you do torch.jit.trace model, you give it the model, and you give it your inputs. I only put 30 minutes in for the session. I know I'm going a lot over time here, so I'm not going to run through that here. But you can get better performance by doing this torch.jit.trace module. It's also important to note that Pytorch also supports automatic mix precision, but it's a little more complex. So if you just search mix precision Pytorch, you can get a good tutorial on how to do that. That's all I have for those two pieces.